So our first example, this is just a simple case of matrix equations, and it is fairly simple. They'll get a bit harder, but there are some things you can't do with matrices that you can do in a number system, so they won't get that much harder. For example, I won't be asking you to solve matrix quadratics. Although that sounds interesting, maybe I'll put it in as a complex sum for me, who knows. Okay, so there we go, we've got P and Q defined. They're 2 by 3 matrices. Remember, we defined the number of rows first and then the number of columns. So it's a 2 by 3 matrix. If we're doing matrix arithmetic, the dimensions of the matrix have to be the same, or the order of the matrix, for the addition and subtraction to take place. But my rearrangement here is that x is equal to q, sorry, negative x is equal to q minus 2p, which means that x is equal to 2p minus q. So I can use scalars like we always have, and I can use general equation solving like we always have. So I've subtracted 2p here, and then I've multiplied through by -1 to make my x positive. But I could do it cell by cell later on as well. And then basically this is equal to 2 times 3 negative 9, 1, 2, 6, 4, minus 0, 1, 1, negative 1, negative 1, 0. And that's equal to 2 times 3 is 6, minus 0 is 6. 2 times negative 9 is negative 18, minus 1 is negative 19. 2 times 1 is 2, minus 1 is 1. 2 times 2 is 4, minus negative 1 is 5. 2 times 6 is 12, minus negative 1 is 13. 2 times 4 is 8, and there's a 0. And so x is equal to that value to make that work. So again, that's just an example of you can rearrange like you always have, and it will come together. And it's actually, if you think about it, it's kind of like solving 6 equations at once. So if you have 6 equations that are defined in the same way, 6 different values for P and Q, such that 2P minus X equals Q, where they're just numbers, well, if we put them in an array, we can solve them all at once. Here's example 4, which is a bit harder, and I might give you a second to have a think about example 4 as well, and see if we can solve it. It's not a matrix quadratic, but it does involve quadratics at one point. So I've written in green here that 4 cells mean that there's 4 distinct relationships, and therefore it can be solved for 4 distinct variables. I want you to think back to our time doing vector components and how we could solve what looked like an unsolvable equation that had 2 variables in it. We could solve it because we could equate the I component and the j component separately and then solve from there. We get the same thing with matrices. We've now got 4 cells, so there are 4 relationships. The top left-hand cell has to be equivalent on both sides when we combine them into one matrix. That gives us a distinct relationship. So in this case, you can actually see, if I go through, the bottom left cell has all the B's, and the top left cell has the A, and the top right cell has all the D's, and the bottom right cell has the C's. So they're actually very distinctly separated. I could mix them up, then you'd end up with simultaneous equations. You could still solve it as long as there's only 4 unknowns for the 4 relationships we can pull out. So I'm going to do some simplifying first, and that is that if I combine the 2 matrices on the left-hand side, I get 10 minus 12, and then I get d squared minus 3d, and then I get 4b minus 9, and then I get 1 minus 3 is equal to A, 10, B, and 2C. And now I can make those individual statements. So statement 1, which will be top left statement, is that 10 minus 12 is equal to A, and therefore A is equal to negative 2. And the bottom left statement, which I'll call number 2, will be 4B minus 9 is equal to B, which means that 3b is equal to 9 and b is equal to 3. And then I get top right, which is the the harder of the four, but not that bad. I get d squared minus 3d equals 10, which means that d squared minus 3d minus 10 equals 0, which means that d minus 5, d plus 2 equals 0, and d could equal 5 or negative 2. And then I get bottom right, cell 4, 1 minus 3 equals 2c, so c equals negative 1. So those specific cells can be equated. And that comes back to a statement I made early yesterday, where I said that two matrices are only equal if all four cells are equal. And so you can use that information to solve equations like this. Are there any questions on that? I'm going to just cut this into two videos.